I'm bringing a little bit of a different problem. Today we'll be doing engineering dynamics, which is, quite an important class for those that are, doing mechanical engineering like I am. And, sometimes other majors do take that class as well. So very important class. But this is a beginner's type of problem in terms of, not necessarily too complex, but at the same time, I wouldn't call it easy. It's just, it has a lot of the fundamentals, right? And we should be able to solve it. And I'll show you how I solve it. I'm not going to use any formulas, okay? I mean, I will use some sort of understanding, but I'm not gonna just use the kinematic formulas. I'm just gonna solve and derive some stuff, and you see. The first thing that we should do is realize that we need to read the problem carefully and pay attention to the picture, right? Especially with this problem, there's quite a bit of things here that we can get confused with. So let's do it. All right, so a golf ball is struck with a velocity of 80 feet per second, as shown. Determine the distance d to where it will land, right? First of all, so we're looking for d, right? Find, great way to start, huh? find, find d, right? The thing is with d is it's being measured, as a slope, right? So we're gonna have to somehow translate that into a coordinate system that we know, right? And then another thing that I could notice right off the bat is that besides having this angle here, which is 10 degrees, they gave us the 45 being measured from that slope. So really, that angle of that initial velocity is what? 55. So be really careful, guys. I mean, these problems a lot of times, they also require a lot of attention, and that's something very important as engineers is to have attention to, like pay close attention to detail. So to solve this problem, right? I mean, let me just finish the last two parts that they want. So we're looking for d, v, okay, a ball struck with velocity of v 80, and then it says later, determine the speed at which it strikes the ground at v. So v final, right? Looking for v final, and time of flight, right? So time of flight is, I'll call it t total, right? So it's the total time, right? So we're solving for these three things, but the first thing that I want to solve for is d, right? Because that will help us solve for the rest. So before I get to actually solving it, I want to show you guys something very important about projectile motion, right? We're assuming no air resistance, okay? No air resistance. We're also assuming no loss, right? We're basically assuming perfect conditions, right? Which means that projectile, which is the golf ball, is going to have a parabolic type of trajectory, right? Orbital parabola. But you guys get the idea. So the point that I'm trying to, show you guys is that the fact that it's parabolic means that the motion is symmetric. So basically, let's just say I number this 1. I'm going to also get a point interest of 2. Call this, obviously, the peak 3, 4, and 5, right? The motion, I mean, whatever happens here at 1 happens in reverse at 5, in a sense. So basically, it's symmetric, right? So it's going to try to mirror the other side, right? So we'll see what I mean by that in a second. But the idea with these type of problems is just to understand that everything, at every point, everything that happens in the x direction happens in the y at the same time. So if there's a change in position in the x, there's going to be some sort of change in position in the y. It's the same object, right? The object is not separated, it's not splitting. So time really is what's going to allow us to relate what's happening in the x with what's happening in the y, right? So that's the idea there. And to complement that idea, I want to show you a little something. So for instance, at launch, our velocity would be something like this, right? The overall, like the resultant, right? So if I break this up, I would get 1 in the y and 1 in the x, right? So now I'm going to start just drawing just the ones in the y and just the ones in the x. I want to kind of prove you something, right? And show you something, I should say. So, providing that, I'm doing an okay job at drawing, you should notice something. I'm going to highlight it. Every component of the velocity in the x direction does not change, neither magnitude or direction. Why? Because there's no air resistance and no loss, right? So, but what happens with the y direction, right? You probably noticed something interesting as well, which is that the magnitude, gets reduced, then it suddenly disappears. There's, no y at the peak, right? Y velocity. And then it suddenly just gets back in, but in the opposite direction, right? I mean, that makes sense because it's going down. So it has to have a component in the y direction, right? Otherwise, it just goes straight forever. So the idea here is that, and when I say that it's a symmetric type of problem, is that the magnitude here is the same one as the magnitude there, okay? But the directions are opposite, okay? And the same thing happens here, magnitude, opposite directions. So as long as you understand that, that's very key, right? Because it allows you to solve all these projectile problems much easier, right? I mean, some of them are a lot trickier than others, but the fundamental is what I'm showing you, right? So with that in mind, let's go ahead and get started, right? So what I'm going to do is I'm just going to kind of replicate what that problem had, right? And what I'm also going to do is, place a coordinate system at launch out of convenience. Let me change that color, right? A little bit better. For convenience, I'm going to place it at launch because then I can track everything from launch and make my life a lot easier, right? So let's just say this is launch and then this is landing, right? At that slope. And then let's just also say that at landing, right? Let me try to change colors. At landing, the height where it lands is d sine 10, and how far away it's from, the beginning, which is, 0 here. On the x-axis, we have d cosine 10, right? So with that in mind, we're going to be able to relate the x to the y position, right? And then finally solve for d. So before we do that, let's derive our equations, right? I don't like memorizing, and I don't think it helps using those kinematic equations. So what we're going to do is we're going to do it from scratch. So x double dot, which is the same thing as d squared x dt squared, in other words, acceleration, is equals to, in the x direction, 0, because there's no change in velocity, right? So easy. X dot, which is dx dt, which is equals to v, right? When I integrate acceleration, right? Imagine in your head, you're integrating, right? So integrate. When we integrate 0, we get a constant c, right? So when we evaluate that constant c, so at t equals 0, right? At t equals 0, there's no t in this equation, right? So really, the velocity is going to be, so v is going to be equals to the velocity initial, which is going to be equal to c, right? And what's the velocity initial? So v initial is equals to 80. So if, just real quick, our vector was 80, and then we have an angle of 55. So we have in the x direction, so vx initial, v initial x is equals to 80 cosine of 55, which is indeed equals to c, right? Now, all I have to do is just sub this information in and get my general equation, which I like to call it x dot 80 cosine of 55. Boom. So this describes the velocity everywhere, okay? Everywhere. Now, to get the position, we just integrate again, okay? Integrate again, and then when we integrate velocity, we get position. So we get 80 cosine, and we're integrating with respect to time, right? Cosine 55 times t, okay, plus c as well. Now we have to stop and realize what's c. So at t equals 0, what do we have? The position is also, so x is equal to 0, right? Because I set, remember, let me scroll up again. I set my coordinate system, I'm even going to bring like an arrow there. I set my coordinate system right there at launch. So the position at t equals 0 is 0, right? In the x direction, 0. Super powerful, okay? So we get that c is also equals to 0, right? Because this term, when I plug in 0 for t, this term right here is going to go away, and then I have that c is equals to 0, right? Because at t equals 0, position in the x is 0. So our general equation for everywhere, when I say everywhere, I really mean it, right? For everywhere in that trajectory of, that golf ball is going to be described by x equals to 80 cosine 55 times t. That's in the x direction, right? Everything here that we did was for the x direction. So what about for the y direction, right? So y direction is no different. We start with y double dot, which we learned that it was the acceleration, right? The dots just mean time derivatives. Derivative with respect to time is equals to, well, we do have an acceleration in the y direction. In fact, we have the acceleration due to gravity, right? Which is, in this case, feet, negative 32.2 feet per second squared. And then when we integrate that, we get y dot, which is velocity in the y direction, just the expression itself, minus 32.2 times t, integrating, right, plus c. So at t is equal to 0, we get that y dot is equals to v initial in the y, right? So when we sub these two informations in, we get that c is equals to v initial y, which is equals to 80 sine of 55. So we plug it in, y dot is equals to negative 32.2 times t plus 80 sine of 55. Boom. We got our expression for velocity. We integrate again to get our position. Okay, this time we get the denominator of 2 because we get the square divided by 2 plus 80 sine of 55. I'm sorry. I don't know why I was thinking 45, 55. T plus c. All right. So same thing. At t equals 0, we have that y is equal to 0 because of the coordinate system convenient that we placed. Right. So at launch, y is equal to 0. So these terms would cancel out. This term would be 0. So c is also equals to 0, right? So when you get good at it, you technically can skip this step, but I don't recommend it because in a lot of problems it will come in handy actually stopping and thinking about it, so I always do it, right? So y is equals to negative 16.1. Let me just simplify this a little bit. T squared plus 80 sine of 55 times t. This is it as far as that expression goes. So what we're left off is with 1, 2, 3, and 4 equations to describe position and velocity everywhere. Okay, these 4 equations literally describe position and velocity everywhere of that golf ball. Okay, it's very powerful, right? So once we do that, we have to remind ourselves what we're solving for. We're solving for D. So let me just redraw this, which was 10. And then remember, D was at, because our coordinate system is like this, which means that, we start at 0, and then obviously there is an x and a y, which gives us a slope, an overall distance in the slope, running in the slope of D, which translates to D sine of 10, and this translates to D cosine of 10, okay? So now that we have these two, we already had it, but I just redid it. What we're going to do is we're going to take the 1 in the x direction, put it here, okay, in the position equation, because remember, this is position, right? D is position. And then we're going to do some stuff, which I'll show you, and we're going to suddenly be able to, not suddenly, I mean, we're working the problem, but we'll be able to relate what's happening in the x to the y, right? So if we do that, d cosine 10, so equation 2, d cosine 10 is equals to 80 cosine 55 times t. If we solve for time, why am I solving for time? Because look, I have time here. So it's convenient and I want to solve for d, right? So t is equals to d cosine 10 over 80 cosine of 55, right? We get that. And then what we do is equation 2 plus equation 4 gives us what? Well, before I do that, let me not skip this step. Very valuable stuff that I have to show. So with equation 4, what I should also be doing is take a point of interest that I use that x, right, which is where we land, right, and replace it. So d sine 10 is equals to negative 16.1 t squared plus 80 sine of 55 times t. And then now, because this position here matches with this position here, let me change colors real quick. Why not? Okay, they match. I mean, everything in that case is happening at the same time, right? Because it's the same position. It's where it strikes the floor, right? So that position in the x and that position in the y are related by what? They're related by the time. They happen at the same time, right? The ball's not splitting. We're not dealing with some sort of crazy, really complicated physics problem where, like electrons are everywhere, sometimes they're here, sometimes... No, it's not that. Everything's happening at the same time. It's one ball, nothing's discontinuous, everything is one piece, right? And then it just travels, okay? So the idea here is that we're going to be able to take this t here and plug it in there because of that, right? So then we get, when we combine, and now I can do what I was planning on doing, plus equation 4 gives us d sine 10 equals to minus 16.1. Let me be careful here. Let me simplify time real quick, okay? Like the actual, well, I'm going to keep it that way for now. D cosine, I just don't know if it's going to fit. It should. 80, see if I don't mess up there. 55, and I have to be careful here because everything is squared, plus 80 sine of 55, ooh, barely gonna make it, times t. Yeah, it's horrible, but I think you guys get it. Now, oh, it's not times t, right? Because I eliminated t. So really, I should have replaced it by the other expression, right? So let me just put it down here. Plus 80 sine of 55 times d cosine 10 over 80 cosine of 55. Okay, now we're good. So this is my new expression, right? And notice that everything is in terms of d now. And it's a quadratic, so I should be able to solve it, no issues whatsoever. What I'm going to do, though, to save us some time, I'm going to plug it all in my solver function in my calculator, which I usually avoid, but in this case, it's worth it. Let me see what I get. So bear with me for a second. I'm working it out as I actually go because I prefer that. We have cosine 10 divided by 80 times cosine 55, and this is squared, Just double check my work here. Alright, makes sense. I just got a pretty small number for some reason for one of the coefficients. So I get minus 0.007415. Yeah, like more like 1/6 t squared, d squared, sorry. Keep referring back to t for some reason. Plus, and then I should combine those terms, all of them, if I can. I get, let me see. Bear with me. Trying to get this for us. Minus sine of 10. Okay, so plus 1.23. Actually, I didn't end up plugging in on the solver, by the way. I said I was going to do it, but I didn't do it. So d is equals to, now I'll plug it in. I was just simplifying. Minus 0.232. Let's see. Alright, doesn't really help what I got here, but I'll simplify it. Over 927, which should simplify into something else. Let me see. Alright, 166.1 feet. Okay, so that's the distance in the diagonal from launch to landing, right? So now that we have that, took me a little while to calculate, I apologize for that. Now that we have that, all we have to do is just take this information and plug it in here, right? Or plug it in the other one, whichever one you prefer, and solve for time. But I'm choosing the first one because it's so much easier. So we get that right here, t is equals to 166.1 cosine 10 divided by 80 cosine of 55. Okay, so times cosine 10 divided by 80 times cosine of 55. Boom. Let me see. 3.56. So that's the total time of flight, by the way. And the reason for that is because we're at strike position, right? We're already hitting the floor back. So at that position, we've gone through all the trajectory that we were supposed to, as far as the physical limitations of the problem. So yeah, we got that time, and then what we do now is to get the velocity, we're gonna have to refer back to our velocity equation. So if you remember, let me pick a different color now if I can, because I wanna make sure that you guys are able to follow what I'm doing. So the velocity equations that we ended up getting, if you remember, was 80 cosine of 55, which means that regardless of time, we always have this velocity in the x direction, and the other one was negative 32.2 t plus 80 sine of 55. Okay, so that is related to time. So how about we do this? Let's calculate y dot at t is equals to 3.56. Okay, so we get that y dot is equals to minus 32.2 times plus 80 times sine of 55. We get that y dot is equals to negative 49.27 feet per second. Okay. Is that the final answer? No. This is just the velocity in the y direction. Okay. Remember, the overall velocity is going to be the combination of both. So the velocity in the x direction is just simply calculating that. So 80 times cosine of 55 45.88 feet per second. And then now, let me change colors one more time just for the answer. Why not? Let's see if this color is going to work. V is equals to the square root of Vx squared plus Vy squared everywhere. But we're interested in V final, right? So we get that square root of minus 49.27. Oh, out of order, by the way. This is Vy. Plus 45.88 squared. And then finally, long problem, huh? V final is equals to, let me see, plus 49.27 squared, square root of that. So the golf ball strikes the floor at a velocity of 67.32 feet approximately, right? I mean, I'm rounding a little bit. 67.32 feet per second. Awesome. That's it, guys. A little bit of a longer problem because, I had to derive the equations and, kind of explain some of the background on how I solve it. The takeaway is, okay, the motion of the projectile motion is, it always resembles something like this, right? It always resembles this parabolic shape. No air resistance, no loss, allows us to, model it that way, right? And with modeling that way, we have to realize that at every single point in this trajectory, so every single one of these points, x and y are going to match in terms of our equations with the same time, right? So things are happening at the same time, as the ball travels. So if you're able to relate things, with time, you're going to be able to get the right answers, right? So that's what I did. Is I related things with time, and I realized, like, hey, the final position gives me a relationship of, something that happens at the same time. That also gives me a relationship of the positions, in terms of the distance d. So after doing all of that, that's it. You just solve for those unknowns, and then you get your answers. But really, the setting up is what really, really matters, right? Because after that, it's just algebra. So I hope this helped. And let me scroll back to the answer real quick, just in case you missed something important or whatever. And that's it, guys. Please let me know how you like this, okay? And give me suggestions of any problems that you want me to do. Thank you so much. Bye-bye.